So we're going to be working today on sections. Why is it so slow? Let me see if it picks up. 5.2 to 5.4. Oh man. All right, we're having all sorts of issues here with me sharing stuff today. So let me see if I can get that working faster. Okay, let's see if this is gonna work faster for us now. Yeah, perfect. Okay, so we're gonna do stuff from sections 5.2 to 5.4. 5.2 to 5.4 just actually breaks down the identities into the different types. So like in section 5.2, the identities we're dealing with are the sum and difference identities. So the whole idea in all of these identity problems, so on all these identity problems, the idea that we're going to be working with is the following. Our goal is we're going to be given some value that we're trying to calculate, and we want to figure out how to do it using only values off of the unit circle. So the values on the unit circle we know theoretically, and so the idea is we're trying to change the values that we're given into things dealing with that are off of the unit circle. So the idea is to use an identity to answer the given question using values from the unit circle. And you're going to see as we go through these problems that we don't always have to use things that, like I might use, say, a sum and difference formula for a problem, but you might, after today is done, be like, well, I would use a double angle formula for that problem. That's okay. So there's not, in a lot of these problems, there's not just one way to do them. There's multiple ways to do them. So as long as you do it an appropriate way, you use an identity correctly, it doesn't matter which identities you use. Oops. So, for example, find the exact value of, okay, so the first one is the sine of 75 degrees. So 75 degrees is not an angle that's on the unit circle. And we're going to right now try to use the sum and product, or the sum and difference identities. So can you think of two angles on the unit circle that when you add or subtract them together, you get 75? Oops, I lost my chat. Yeah, 45 and 30. So exactly. So the sine of 75 degrees, I could really think of this as the sine of 45 degrees plus 30 degrees. And 45 and 30 are both on the unit circle. And so now what I want to do is, now that I know that I can think of 75 as these two added together, what I'm going to do is I'm going to go to the sheet, right? So I have the sheet printed out here. So I'm going to go to the sheet and I'm going to try to look for something that kind of looks like the sine of one thing plus another thing, okay? So if you have the sheet printed out in front of you, or if you go back after class and you look at where I put that handout up, you will see that there is an identity that looks like this. It says the sine of alpha plus beta is equal to the sine of alpha cosine of beta plus the cosine of alpha sine of beta. Okay, so that pink line came directly off of the identity sheet that is listed under the handouts on our Canvas course, right? So I just copied it verbatim. I'm going to do this all day long today. Every time I take something off that sheet, I'm going to write it down in the pink, so you know that when it's written in the pink, it came directly off the sheet. That's the only thing I'm going to use pink for today. So in this case, right, this 45, the 45 degrees is acting like my alpha, and the 30 is acting like my beta. So I'm going to plug them into my formula. So this is going to be equal to the sine of alpha, which is 45 degrees, the cosine of beta, which is 30 degrees, plus the cosine of alpha, so the cosine of 45 degrees, times the sine of beta, so the sine of 30 degrees. So questions about where any of that I've done so far has come from? Okay, so most of today is just going to be doing this thing of pulling stuff off of the sheet. Okay, so if I look here, sine of 45 degrees, right? So anybody remember what the sine of 45 degrees is? Okay, root 2 over 2. So root 2 over 2. And the cosine of 30 degrees would be what? Root 3 over 2. Plus the cosine of 45 degrees is root 2 over 2 again. Yep. And then the sine of 30 degrees is 1/2. Yep. Okay, so if I put these together, right, remember when you're multiplying fractions, you multiply across the top and then you multiply across the bottom. So in this first one here, across the bottom is a 4. Across the top is root 2 times root 3, right? So root 2, root 3. Plus I have here root 2 over 4. Root 2 times root 3 I could simplify. Since they're both under the roots, I can put them together. So this is actually going to be root 6 over 4 plus root 2 over 4. And that is going to end up being root 6 plus root 2 all over 4. I cannot combine the two square roots on the top together. I can't make it root 8. So you can only combine the square roots if they're multiplied times each other. So this root 6 plus root 2 over 4, that's my final answer. Questions? No. Yeah, so to be able to add it, so to be able to add the two together, they have to be essentially be like terms. So like if I had like 3 root 2's plus 4 root 2's, I could add those together and say that that is 7 root 2's. So you want to think of the root 2 like a variable. So kind of just like if I had 3x plus 4x, that would be 7x. When I have root 6 plus root 2, it's almost like saying this is some variable x and this is some variable y. And you can't add those, you can't do anything besides it's just x plus y. So we have to leave it as just root 6 plus root 2. Other questions? Okay, so how I got root 6 is because, so here I have root 2 times root 3. And since they're both square roots, basically there's kind of like a middle step in here that I didn't write, but it's basically I can write it as a square root of 2 times 3. And then 2 times 3 is 6, but it's still under the square root. Does that help with how I got root 6? Okay, so then, wait a minute, I just got a bunch of questions, so hold on a second, let me make sure I answer all these. Let's see. Okay, would we do the same thing if we needed to find the sine of 15 degrees? Yeah, so if you needed to find the sine of 15 degrees, you could think about 15 degrees being 45 minus 30. So yes, exactly. And break it up that way. And then somebody asked me, what would root 2 plus root 2 be? So root 2 plus root 2, this would be 2 root 2's, right? So it's like I have one apple plus one more apple, I'd have 2 apples. So it's the root 2 is like the like term. So 1 root 2 plus one more root 2 would give us 2 root 2's. Does that help with that question? No problem. Any other questions? No. Okay, and we're going to do more problems here. Okay, so B, the tangent of 19 pi over 12. So when they're given in the pies, right, sometimes it's a little easier if you convert it to degrees to think about the degrees on the unit circle. You can do it in terms of radians, right? So if I wanted to, I would need to be thinking, well, to get a 12 in the denominator, I'd probably need some combination of something over 4. So one of the, like, some number of pi over 4s plus some number of pi over 3s, or subtracting them. So you one or the other. But I actually think in these problems it's a little easier to change it to degrees. So we know how to change to degrees, right? So if I have 19 pi over 12, I can do 19 pi over 12 times 180 degrees over pi, and if you work that out, this turns out to be 285 degrees. So finding the tangent of 19 pi over 12 is the same as finding the tangent of 285 degrees. And that makes it a little easier to work with when we think of the unit circle. So can you think of two numbers on the unit circle that if you add them together, you either get 285, or if you subtract them, you get 285? Okay, so 30 and 315, right? So if I take 315 and I subtract from 315 30, right? Then I would end up with 285. Right, we okay with that? So this is going to be the tangent of 315 degrees minus 30 degrees. Okay, so 150 and 135 would have worked. You could have added those two together. So there's lots of angles sometimes that work, right? So 30 and 315 just happens to be one of them. Like Liana said, 150 and 135. On my paper, I actually had 240 and 45. So there's lots of combinations that can work. So you're not necessarily tied to one combination that works. You just have to find one. Even though I had 240 and 45 on my paper, I actually kind of like the 315 and the 30 this time, just to be able to show you one that's a subtraction. But they all work the same way. It's just a matter of finding the right formula then on the sheet. So if I go to that sheet that I've posted on Canvas, right, and I look, you'll see there's one that says the tangent of alpha minus beta. And so the tangent of alpha minus beta ends up being the tangent of alpha minus the tangent of beta divided by 1 plus tangent alpha tangent beta. So in our case, our alpha is 315 and our beta is 30 degrees. So this is going to be the tangent of 315 degrees minus the tangent of 30 degrees divided by 1 plus the tangent of 315 degrees times the tangent of 30 degrees. Okay, so tangent of 315 degrees. What's the tangent of 315 degrees? Yeah, -1. So we have -1 minus What's the tangent of 30 degrees? Yep, 1 over root 3. So minus 1 over root 3, all divided by 1. Plus, again, tangent of 15 degrees is minus 1. Tangent of 30 degrees is 1 over root 3. Okay. Alex is not going to take this answer, I don't think, because you have little fractions on a big fraction, right? So we have a complex fraction. And so we really would like to get rid of the complex fraction. So the thing that's making it a complex fraction is this square root of 3 in the bottom, right? So I would like to get rid of this square root of 3 in the denominator. So what I'm going to do is I'm going to multiply the top and the bottom by the same thing. As long as I multiply the top and bottom by the same thing, that's okay. So I'm going to multiply by the square root of 3 so that I can clear that out of the denominators. Now, when I multiply times the square root of 3, it has to go times each piece, right? So each term. So times the first term times the second term. So on the top, we're going to end up with a minus root 3. And then in the second piece, when I take minus 1 over root 3 times root 3, the root 3's would cancel. And I'd end up with minus 1 over. Same thing in the bottom. It has to multiply times the first term. And then it also has to multiply times the second term. Now, the second term happens to have two things multiplied together. You don't have to multiply it times each of them, right? When we do multiplication, you know, if I do 2 times 5 times 7, I don't do 2 times 5 and 2 times 7. I just do 2 times 5 is 10, 10 times 7 is 70. So same thing here, I just have to multiply them all together once. So in the first term, I end up with square root of 3 times 1, which is root 3. The second term, the root 3's would cancel, and I'm just going to be left with minus 1. So I end up with minus root 3 minus 1 over root 3 minus 1. And you can leave your answer like that. It's okay to have radicals in the denominator. I don't make you rationalize it. Alex does not make you rationalize it. So that is a perfectly fine final answer. We just don't want those little fractions. We don't want like a big fraction that has little fractions as well. Questions? How did I get negative 1 on the denominator? Okay, so the negative 1 on the denominator came from, I have this going on. I have negative 1 times 1 over root 3 times root 3, right? The negative 1 came from this part here. This part times the root 3. So that's what I've written down there. So what happened here was just the root 3's cancel, and I had negative 1 times 1, which would be negative 1. No problem. Alex, where did I answer your question, or where are you talking about? Okay. Any other questions before we do another problem? Okay, so alright, so let's try this one. Cosine 35 pi over 18 times the cosine of 5 pi over 18 plus sine of 35 pi over 18 times the sine of 5 pi over 18. So 35 pi over 18, 5 pi over 18. These are values that are not on the unit circle, so I can't just look up the individual values. But again, I can make use of some of those identities that are on the sheet. Sometimes, so the last two problems, we were looking for like the left side on my sheet. It gave me that first part and then said it's equal to the second part. In this case, this is looking more like the second side of my sheet, and that's okay. I can rewrite the identities in either direction that I want. So this looks a lot like, if you think of calling this part here, oops, let me do it in another color. If you think of this as an alpha and this as a beta, right, then this looks a lot like cosine alpha, cosine beta, plus sine alpha, sine beta. And if you look at the sheet, cosine alpha, cosine beta, plus sine alpha, sine beta, that's actually the same as the cosine of alpha minus beta. So that at least gives us a starting point. Maybe if I take alpha and I subtract off beta, I'll actually get something that I happen to know. So if we try that here, we would end up with the cosine of alpha, 35 pi over 18, minus the cosine of beta, which is 5 pi over 18. And if I take 35 pi minus 5 pi, I'd be left with 30 pi. So this becomes the cosine of 30 pi over 18. And you might go, well, 30 pi over 18 is not on the unit circle. But what I would say to you is, well, we might have to reduce 30 pi over 18. So if we think about, can we think of some number that goes into both 30 and 18? Yeah, 6. So 6 goes into 35 times. 6 goes into 18 3 times. So this is really the same as the cosine of 5 pi over 3. And is 5 pi over 3 on the unit circle? Yeah. So now it's just a value on the unit circle I have to look up. So what's the cosine of 5 pi over 3? Yeah, 1/2. So my final answer here is just 1/2. So even though it started off looking pretty crazy with those 35 pi over 18s and the 5 pi over 18s, it actually just settles down into a nice kind of value here. Questions? No, so these problems are not proof problems, right? So last class we did the proof problems. The problems that you're going to have to do in terms of the homework for proof are going to be those. Different people teaching trigonometry do different things. So there are professors who teach trigonometry or pre-calc 2, which is trigonometry, that make you do proving identities throughout all of the identity pieces. I don't. I do a little bit of proving identities in section 5.1, and then we're done with proving identities. Everything else that we're doing is just applying the identities and using the identities to help us out, because that's really what people do with identities, right? Once you leave pre-calc 2, no one's really going to ever ask you to prove an identity ever again. So rather than spend a ton of time on proving identities, which I think is kind of a waste of our time, I like to spend more time on working with the identities. Does that answer your question? No problem. And just in case, usually, I think I showed you guys that identity sheet last class and somebody asked me, but just in case either you weren't here or you don't, or I'm flipping around classes of mine, you do not have to memorize that identity sheet. So on the next test, I will allow you to have that identity sheet. You can print it out before the test. I'll also put it up with the test. So you can have the identity sheet. do not have to, so you can have the identity sheet. If you're going on to take calculus, then knowing the ones that I had in the box, the quotient identities, the Pythagorean identities, knowing those off the top of your head are really important because we do use them a bunch. So just kind of be aware that if you're going on to take another math class, like you should know the ones that are in the box. But just because we're in this, and generally I usually remove the box for the test, but because we're in this online environment and to make everything kind of fair for everybody, I'm just going to give them all to you on the next test. So, questions before we go on and do a different type of problem? No? Okay. All right. So, we're going to look at a couple others here. So that was C, so D. The sine of 75 degrees minus the sine of 15 degrees. So, again, I have the sine of 75 degrees minus the sine of 15 degrees. 75 degrees isn't on the unit circle, 15 degrees isn't on the unit circle. So I'm trying to find something on my sheet that reflects sine of one thing minus sine of something else. And so there is under the sum to product identities on that sheet, there is an identity that says the sine of alpha minus the sine of beta is equal to 2 sine of alpha minus beta over 2 cosine of alpha plus beta over 2. And so again, we're just going to plug our stuff in, right? So this is going to be 2 sine, our alpha is 75, so 75 degrees minus 15 degrees over 2 cosine of 75 degrees plus 15 degrees over 2. So this is going to be 2 sine, 75 plus 15 is 90, and 90 divided by 2 is 45, right? Oh, 75 minus 15. I added 15. I'm like, that doesn't match up with what's on my paper. 75 minus 15 is 60. 60 divided by 2 is 30. So this is the sine of 30 degrees. Cosine, okay, 75 degrees plus 15 degrees is 90 degrees. 90 divided by 2 is 45. So plus the cosine of 45 degrees. And so we just have 2. The sine of 30 degrees is 1/2. And the cosine of 45 degrees is root 2 over 2. So one of these 2's would cancel. And so this just ends up being root 2 over 2. Questions? So once you find the right identity on the sheet, they're actually not too terrible. But it's just you have to find the right identity to use to begin with. Should we do another one? I'm kind of just asking to make sure people are at least, you know, I'm talking to live people, right? Not just screens. All right. So I got a couple answers there. All right. So E, what about the sine of 17 pi over 12 times the sine of pi over 12? So again, 17 pi over 12, pi over 12, those are not values on the unit circle, so I can't just look them up, right? If they were things on the unit circle, I could definitely just look them up, but here I can't. So again, I want to go to my sheet. I want to find something that looks like the sine of alpha times the sine of beta, and that is under product to sum identities. So sine alpha sine beta is going to be equal to 1/2 times the cosine of alpha minus beta minus the cosine of alpha plus beta. And so in this case, I just have to, again, plug stuff in. So we have 1/2 the cosine, so alpha is 17 pi over 12 minus pi over 12 minus the cosine of 17 pi over 12 plus pi over 12. So we have 1/2 times the cosine, so 17 pi over 12 minus 1 pi over 12 would give us 16 pi over 12 minus the cosine, 17 pi over 12 plus pi over 12 would give us 18 pi over 12. And I can reduce those, right? So 16 and 12, 4 goes into both of those, right? So 4 goes into 16 4 times, 4 goes into 12 3 times. And 18 and 12, 6 goes into, so 6 goes into 18 3 times, 6 goes into 12 2 times. So this is the same as 1/2 times the cosine of 4 pi over 3 minus the cosine of 3 pi over 2. So we get 1/2 times the cosine of 4 pi over 3 is minus 1/2. And what's the cosine of 3 pi over 2? Yeah, 0. Somebody told me. So I have 1/2 basically times minus 1/2. So this is going to be minus 1/4 as my final answer. Questions? No. Okay, so let's try. What was that? E. Okay, F. So F here, 2 cosine squared of minus 165 degrees minus 1. So again, 165 degrees is not one of the values. Oh, no problem. Yeah, I can totally, yeah, if I'm going too fast, definitely tell me. So let me know when I can go back to the next page or start the next one. As I think I've said before, right, that's one of the downsides of teaching online. I can't see you guys, your faces, and whether or not you guys are like looking at me ready to go on to the next problem, or if you're still writing. So no problem. Anybody else need me to wait before I go to the next page? No? Okay. Okay. So my new problem here is 2 cosine squared of minus 165 degrees. So minus 165 degrees, the minus just means we're rotating in the clockwise direction, right? So 165 degrees or minus 165 degrees, they are different, but neither one of them is actually on the unit circle. So hopefully this... Okay, that's a good question, Sivan. So no, let me write that in on a side note here. 1 second, let me finish the train of thought on the one. So cosine of minus 165 degrees. So hopefully this problem here is going to look like something that is on my sheet, on my identity sheet. So I will come back to the cosine of A plus B. So give me a minute. Let's finish this problem and then we'll talk about that. So if I look on my sheet, there actually is an identity that says 2 cosine squared theta minus 1. And that actually is going to be equal to the cosine of 2 theta. So there is something on my sheet that looks just like this. And so in this case, my theta, right, most of the ones on the sheet are written in alphas and betas, but there are some that are written in thetas. So 2 cosine squared theta minus 1 being equal to the cosine of 2 theta, that's going to say that this is equal to the cosine of 2, and my theta happens to be minus 165. So 2 times negative 165 degrees. Or we're looking for the cosine of negative 330 degrees. So negative 330 degrees is on the unit circle. Negative 330 degrees, just to kind of refresh yourself, right, would go around this way and it would end up here in the first quadrant someplace. So this is negative 330 degrees. Negative 330 degrees is going to be the same as 30 degrees, right? Because you end up landing in the same spot. Going this way would give us 30 degrees. So the cosine of negative 330 degrees is going to be the same as the cosine of 30 degrees, which is going to be root 3 over 2, right? Yeah, I thought that might be what you were trying to say, Braxton. Okay, questions on this one? No. Okay, so going back for a second, Sivan asked, is the cosine of A plus B, is that the same as the cosine of A plus the cosine of B, right? And the answer is no. So you cannot split up a cosine, a sine, a tangent, a secant, a cosecant. You can't break it up that way, right? If we could break it up that way, we wouldn't need this whole sheet of identities. So this is not true. What is true is that the cosine, and this comes right off of the sheet, right? So on the sheet, rather than A's and B's, it's written as alphas and betas. But the cosine of alpha plus beta is the cosine of alpha cosine of beta minus the sine of alpha sine of beta. So it's not just, you can't just take a cosine if you're trying to find the cosine of two things and split it apart and just find the cosine of each of those things and add them together. You're not going to get the right answer. Does that help? No problem. Other questions? Okay. So if the cosine of x is equal to negative 4/5 and x is in quadrant 3, find, so we're going to find a couple things. The first thing we're going to find is the sine of 2x. I'm going to leave a little bit of room here between these. The second thing we're going to find is the cosine of 2x. And then we'll put c over here. We also want to find the tangent of 2x. So I want to find these three things. I want to find the sine of 2x, the cosine of 2x, and the tangent of 2x. So sine of 2x, cosine 2x, tangent 2x, those are all formulas that are on that trig identity sheet. So if I take the sine of 2x, the sine, this matches up with the sine of 2 theta is 2 sine theta cosine theta. So that's right off of the sheet, right? So again, anything written in pink today is coming directly off of that trig identity sheet. So sine of 2x is going to be sine 2 theta, or I'm matching it up with the sine of 2 theta, so 2 sine theta cosine theta. Which means this is equal to 2, instead of thetas, we have x's. So 2 sine x cosine x. The cosine of x, I happen to know is negative 4/5, right? So we're going to have 2 times something times negative 4/5. The problem is I don't know what that something is. However, they gave me enough information at the beginning of the problem to figure that out. So they told me at the beginning of the problem that our angle theta, or not theta, x, happens to be in the third quadrant. So I have some angle that's coming down here, we're calling this x, in the third quadrant. And they told me that the cosine of x is equal to negative 4/5. So remember, cosine is adjacent over the hypotenuse. So the adjacent, we're going to have a 4. The hypotenuse, we're going to have a 5. Now, you notice I didn't write the negative at first. So the reason I didn't do that is because I want to figure out where the negative should go. So remember, the negative is never on the hypotenuse. And so the negative in this case would have to go with the 4. And then I can use the Pythagorean Theorem to find that missing side, right? So a squared plus b squared equals c squared. And remember, the c always has to be the hypotenuse. So in this case, we'd have negative 4 squared plus b squared equals 5 squared. And it doesn't matter whether you made the negative 4 the a or the b. The a and b doesn't matter which is which, but the c has to be that hypotenuse. So this is going to be 16 plus b squared equals 25. So b squared is going to be 25 minus 16, which is 9. So b is going to be plus or minus the square root of 9, which is plus or minus 3. So the number value for that straight up and down part is going to be a 3, and then I have to figure out whether that should be a positive or a negative. So since it's going down, should it be positive or should it be negative? Yeah, it should be negative. So there's my triangle, and now that I have that triangle, I can easily figure out what the sine of that triangle is. So what is the sine of x? Yeah, negative 3/5. So that's what should go in here, negative 3/5. So if I multiply these all together, remember you can think of this as 2 over 1. So on the top I have 2 times negative 3, which is negative 6. Negative 6 times negative 4 is a positive 24. And on the bottom I have 1 times 5 is 5. 5 times 5 is 25. So my final answer for the sine of 2x is 24 over 25. Questions? The other values work the same way. So if I'm looking for the cosine of 2x, now, if you go to the sheet and you look for the cosine of 2x, there are 3 different cosine of 2 thetas, and you could pick whatever one you want. There is the cosine of 2 theta, so I'll write them up here. This way you can see what I mean. If you went to the sheet and looked, you'd see the cosine of 2 theta is equal to cosine squared theta minus sine squared theta. Also, the cosine of 2 theta is equal to 1 minus 2 sine squared theta. And the cosine of 2 theta is equal to 2 cosine squared theta minus 1. So you could use any one of those that you want, right? There happens to be 3 different ones. It's not like one of them you use one time and one of them you use a different time. They all are going to give you the exact same answer, so it doesn't really matter which one you use. So we could just use the first one. We already know what the sine and the cosine are, but you could try it, right? I'm going to use the first one. If you want to use the second one or the third one and try it, you'll see you get the same answer. So we're going to use that the cosine of 2 theta is cosine squared theta minus sine squared theta. So in our case, this is going to be cosine squared x minus sine squared x. So the cosine of x is minus 4/5, and we're squaring that. Minus the sine of x is minus 3/5, and we're squaring that. So we end up with 16 over 25 minus 9 over 25, or 7 over 25. Questions? So kind of like I said, a lot of these are just about trying to find the correct part on the units, or find the right identity on the trig sheet. So the tangent of 2x, if you look at that sheet, there is one that says the tangent of 2 theta, and the tangent of 2 theta is 2 tangent theta divided by 1 minus tangent squared theta. So in our case, that's going to be 2 tangent x divided by 1 minus tangent squared of x. So what is the tangent of x? Yeah, 3 over 4, right? It's minus 3 divided by minus 4. So the two minuses will cancel each other out. So we have 2 times 3/4 divided by 1 minus 3/4 squared. I'm going to move this kind of up and over a little bit here, just so I have a little more room. So on the top here, right, 2 times 3/4 would give us 3/2. So I have 3/2 divided by 1 minus 9 over 16. So again, Alex is not going to let us put that answer in. We have those little fractions as part of a bigger fraction. And so I want to clear the denominators. In this case, if I multiply top and bottom by 16, it'll get rid of all the denominators. So that's what I'm going to do. I'm going to multiply this top part by 16, and I'm going to multiply the bottom part by 16. On the top, the 2 and the 16 would cancel each other out, and I'd have an 8. So I just have 3 times 8, which is 24. On the bottom, I have to distribute the 16. So I have 16 times 1, and then I also have 16 times this negative 9 over 16. So I'd end up with 16. In the second part, the 16 in the little denominator and the 16 would cancel each other out, and so I'd have minus 9. And so that gives us 24 over 7. Questions? It doesn't matter. You can use whatever one you want. So there's not a specific one you have to use. So you didn't have to use the same one I did. You could have easily just did the 2 cosine squared theta minus 1. If you had used that, 2 cosine squared theta minus 1, I just picked it because it's the third one and we can still see it up here. If you had picked that, right, we would have had 2. The cosine we said is negative 4/5. So I would have had 2 times negative 4/5 squared minus 1. So this would give me 2 times 16 over 25 minus 1. Or 32 over 25. And you could subtract off 16 over 25. And if I did that, I should, oops, not 16 over 25, 25 over 25. I'm like, wait a minute, something's wrong here. So 1 is the same as 25 over 25. And then if you do 32 minus 25, you would get 7 over 25. So no matter which one you do, you end up with that 7 over 25. Does that make sense? No problem. Other questions? Can I go to the next page? I just want to make sure I don't want anyone to feel like they're rushed. Okay. All right. So let me keep recording. Okay. So one of the things before I do the next set of examples, I want to go back and pull back up that, sheet because I want to point something out on the sheet before we do the next set of problems. Okay, so the next ones that we are going to do are going to come from these half angle identities. Whoops. My touchpad does not like me today. Okay. So if you look at these half angle identities, you will notice that here, these are the 3 main ones we really use. We don't really use the sine squared, cosine squared, or tangent squared. We will use this tangent of alpha over 2 because it doesn't have this funky plus or minus. But if you notice, I have this part here and it says plus or minus, and it says that the plus or minus depends on the angle. And so what that means is when we're doing the problem, we actually have to, depending on each individual problem, it could be a plus or it could be a minus. And we have to figure that out, okay? So where every other identity on this whole entire sheet, it's literally just a plug and chug. These three, if I'm trying to use these half angle identities, I actually have to stop and think about what is going on and determine whether or not I have a positive. My answer should turn out to be positive, or my answer should turn out to be negative. And so we're going to do a couple examples, and it'll make more sense what I'm talking about, but I want you to be aware that it has this plus or minus part. So, okay, so, for example, find the exact values of A, the cosine of 112.5 degrees. Okay, so 112.5 degrees, not something that is on the unit circle, right? So it's not a value that I'm just going to be able to look up. However, if you were to double 112.5 degrees, right? What is 112.5 degrees doubled? Okay, right, 225. And 225 does, in fact, happen to be something on the unit circle. So this 112.5 happens to be the same as the cosine of 225 degrees divided by 2. Right? So, and that's good because 225 degrees happens to be on the unit circle. Okay, so if I look, there is that formula that says the cosine of alpha over 2 is actually equal to plus or minus the square root of 1, let me pull the right one, plus the cosine of alpha all over 2. Okay, so I went to my sheet, I pulled off the problem from my sheet, but I have to decide whether I need to use the positive case or the negative case. Okay, so the thing people get confused about on these problems the most is which angle am I worrying about what quadrant it's in. And so it's always going to be your original angle. So if we think about this angle here, 112.5 degrees, which quadrant is 112.5 degrees in? Right. So this is in quadrant 2. And in quadrant 2, are the cosine values positive or negative? Yeah, so in quadrant 2, the cosine values are negative, right? Remember our little thing, all students take calculus, right? So we're talking about the sine or the cosecant. Those are the only things that are positive. So the cosine is going to be negative, which means my answer, I'm going to use the negative 1, okay? So this is going to be equal to, or I should put it underneath. So this is going to be equal to negative the square root. So my alpha in this case is 225. So negative the square root of 1 plus the cosine of 225 degrees all over 2. Okay, so now I just have to look up what's the cosine of 225 degrees. Minus root 2 over 2, yep. So this is going to be equal to minus the square root of 1 plus minus root 2 over 2, all divided by 2. Again, it's okay that I have roots under roots. That's not a problem. It's that little fraction as part of a bigger fraction. So to get rid of that, I'm going to multiply the top stuff all by 2. And I'm going to multiply the bottom stuff, which is just one thing, times 2. So this is going to be negative the square root So when I multiply times the first one, 2 times 1 is 2. I have a plus, then a minus, so that's just going to be a minus. In that second piece, the 2's would cancel, so we just have 2 minus root 2. And on the bottom, it's all over 4. I am definitely okay with you leaving that as your final answer. Alex, I believe, would accept that as your final answer, but it might tell you, hey, you can simplify it a little bit more. We can split a square root up into the square root of the top, divide by the square root of the bottom. So this is actually minus square root of 2 minus root 2 over the square root of 4. So you're allowed to split up square roots if they're multiplication or division. You can't split up the addition part or subtraction part. And then in this case, the square root of 4, we do happen to know it's 2. So this is going to be minus square root of 2 minus root 2 all over 2. And usually at this point, people want to try to cancel things, but you can't cancel anything out because the 2's in the top, one is under just the first square root, one is under a double square root. So you cannot cancel them out. Why is it square root of 4? So it's 4 because here I have a 2 and here I have a 2. So that 2 times 2 gives me the 4. And then I split it up into the square root of the top divided by the square root of the bottom. Does that answer your question? No problem. Other questions? So on these problems, we just have to be a little careful that we're picking the right part, right? So that's kind of really the most important piece of information, that we are picking off the correct thing. So let's try another problem. So, B. So find the sine of alpha over 2 given that the cosine of alpha is equal to 12 over 15 and alpha is between 3 pi over 2 and 2 pi. Okay, so again, I am going to go to my sheet. So I'm looking for a sine of alpha over 2. So the sine of alpha over 2 is equal to 1 minus the, plus or, sorry to write the wrong one. So it's equal to plus or minus the square root of 1 minus the cosine of alpha all over 2. Okay, so the first thing we have to do is we have to figure out what quadrant alpha over 2 is in, right? I know that alpha is between minus 3 pi over 2 and 2 pi, right? And again, sometimes this is a little easier to do if you think of it in terms of degrees. So remember, 3 pi over 2 is 270 degrees. So we're saying that alpha is between 270 and 360 degrees is 2 pi, right? So that's where alpha is. I'm interested in alpha over 2. So to figure out where alpha over 2 is, I want to take all of those things and divide them by 2. So I'm looking for alpha over 2, which means alpha over 2, if alpha is between 270 and 360, alpha over 2 has to be between those two numbers divided by 2. So 270 divided by 2 is 135 degrees. So 135 degrees is less than alpha over 2. And 360 divided by 2 is 180 degrees. So which quadrant are we talking about then? If I'm somewhere, if my angle's between alpha over 2 is between 135 degrees and 180 degrees, which quadrant am I in? Yeah, so this is all in quadrant 2. And if I'm in quadrant 2 again, or was last time? I can't remember. See, I can't remember already my last example. Yeah, my last example was in quadrant 2 as well, right? So in quadrant 2, we said the cosine is negative. So we're dealing with the negative one here, right? So if they give you the angle alpha, like I did in the last example, that's easy. You can just pick off. You can just say what quadrant it's in. But if they give you a bound for alpha, you have to do this dividing thing to figure out what quadrant it's in. So if I do this, this is going to be equal to negative the square root of 1 minus the cosine of alpha all over 2. Okay, so it's negative because we're looking for quadrant 2. So remember, in quadrant 2, there's all students take calculus. The only things that in quadrant 2, the only things that are positive are the sine. The S stands for the sine. And then to go along with the sine is the cosecant, right? So those are the only two values that are positive. So everything else in quadrant 2 is negative. And since my angle that I'm looking for, it happens to be in quadrant 2, then I know that I have to take the negative part. It's not that you're using the cosine value to determine. Oh, thank you. I'm sorry. Yeah. I'm ahead of myself, right? I want to use the cosine, but I didn't go back and read the original problem. So yeah, you guys are all right. Let me erase this. Let's say this again. I'm jumping the gun. Sorry. Okay, this is plus or minus. I am looking for the sine, right? And in quadrant 2, the sine is positive. So, right, this part is in quadrant 2, and the sine is positive in quadrant 2. So I want the positive part. So this is going to be positive. Sorry about that. Now that I've confused everybody, right? Make sure you go back and look at what you're trying to figure out, rather than just assume you're figuring out the cosine again, right? So since I'm figuring out the sine, and the sine is positive in quadrant 2, my answer, we're going to take the positive one. And then in this case, we happen to know what the cosine is, right? So the cosine of theta, or of alpha, is 12 over 15. So this is going to be the square root of 1 minus 12 over 15 all over 2. So this is going to be the square root of, so again, I want to get rid of that little 15. So we're going to multiply the top by 15, multiply the bottom by 15. So we have 15 minus 12 all over 30. 15 minus 12 is 3. So I have the square root of 3 over 30, or the square root of 1/10. And you can leave the answer like that. If you want to, you could break it up and make it square root of 1 over square root of 10, which would be 1 over the square root of 10. So any of those answers, if you really wanted to rationalize it from there, you could, but any of those would work. Questions? So you just got to be a little careful on those half angle identities that have that plus or minus. So there's still a little bit of the identities. There's one other type of problem which I didn't show you at all yet, which does pop up in the homework, and that is the problem asking you to figure out it'll give you it'll give you stuff and there's no actual angles anywhere. It'll say like write this as an expression of x, or write this as an expression of v. So we haven't done any of those problems. And so 3 minutes is not enough time to do one of those problems. So next class, I will start with one of those problems, and then we'll start section 5.5. And section 5.5 is going to take us 2 days. So it'll be good. It's a good working to be able to finish this one little part from these sections 5.2 to 5.4, and then to do just that one part of section, or do part of section 5.5, and then finish the rest of section 5.5 the next class. So that's kind of the game plan. Section 5.5 is the end of the material for the second test, right? So our second test, I believe, is let me see, I think it's the Wednesday before spring break, right? So yeah, March 22nd sounds right. I have the sheet here in front of us. Yeah, the 24th, actually. So the 22nd is the Monday. On the 22nd, we'll review. And then the second test will be the 24th. And then you'll have spring break. So you kind of get like a whole break of math, right? So there's not anything you have to do over spring break for math, which is kind of nice, right? I planned it that way. And then we'll pick up with like kind of the end stuff after spring break. So yeah, so what we're going to do is we're going to do section 5.5 kind of the next 2 days. And then on the 17th, March 17th, we actually won't have class because I have an appointment that I could not change. So it kind of gives you an extra day there to practice. I'll give you the review sheet before then. That way you can practice the review sheet and try the problems on the review sheet during that day when we don't have class. And then the 22nd, we'll review for the test. And then the 24th, we'll take the test. And I'll remind you again next week about not having class next Wednesday. So we do have class this Wednesday, right? So 2 days from now, I will be here. I will be teaching stuff. It's St. Patrick's Day, the 17th. So it's nice that it happens to be St. Patrick's Day. I can just say, oh, it's St. Patrick's Day. We don't have class. But just so that you're aware of that. So any questions? No? All right. Well, have a good rest of your day, and I'll see you on Wednesday.